Hello, everyone, and welcome to another lecture in this online version of Transitions to Advanced Mathematics, Math 3325 at the University of Houston. And so today we're going to continue our discussion, our march through Chapter 4 of the textbook regarding functions. And last time we talked about bijections and inverses and what kind of neat properties we can describe about functions in the case that they're bijections, in particular with regards to them having inverses. But today we're going to look at another special type of function, namely sequences, which are very, very important in the study of, in particular, real analysis. So sequences play a central role in the representation of functions using infinite series. So this is back to your calculus days. You can use sequences to represent functions as infinite series, and we know that that can be useful. But they also characterize a number of important properties of real numbers. And so today we're going to spend some time laying the foundation for the ideas behind sequences. And in particular regarding what it means for a sequence to converge or diverge. And so while you're going through this lecture, I want you to think of everything in terms of errors and, in terms of errors. So think of material in terms of errors, or how close an answer is. How close an answer is to a true value. Some of you all are going to be scientists or engineers in some capacity, and whenever you run experiments or you design some contraption, a lot of times you like to design the contraption so that it falls within some range, some error bound of some true value you're trying to achieve. Many times, and particularly in the applied mathematics and applied sciences, you can't achieve an exact answer. So oftentimes we just have to do with approximations and getting an answer reasonably close. And so that's what we're going to think of, as we'll see in a bit here, of in terms of sequences. Okay? So let's quickly recall what a sequence is. We defined it in section, I think, 4.1 when we were considering sequences, or considering general functions. A sequence is a function whose domain is the natural numbers. So if x is a sequence, and x is acting on a natural number n, okay, the image of n is denoted x sub n instead of x sub n. This is just for sequences. And is called the nth term of the sequence. So the image of the nth term under the sequence x is going to be the nth term of the sequence x, right? So at the very basic level, a sequence is simply a function whose domain is the natural numbers. Okay, and so some examples, we can always look at, some very simple examples. So xn equals 2n minus 1. This is the sequence of odd positive integers. Right? Sequence -1 to the n is just a sequence that looks at something like follows: -1, 1, -1, 1, oops, 1, -1, 1, dot, dot, dot. So every even term in the sequence is 1, and every odd term is -1. We can also look at some more interesting examples. So xn equals, say, -1 to the n over n plus 1. And when you're given a sequence, a lot of times what one is interested in is to know is what happens as n gets large. Does the sequence level off somewhere, or does it just grow without bound, or does it oscillate, as in the previous case, between -1 and 1? What is the behavior as n gets large? So what is behavior as n gets large? Well, we can just write down some terms of this of the sequence here. We know that x1 is -1/2, x2 is 1/3, x3 is -1/4, x4 is 1/5, and you can continue the sequence. And x sub 99 is -1 over 100, and then if you keep going, x sub 1000 is going to be 1 over 1001. So what seems to be happening is terms are getting closer to 0. Right, so we can actually draw this as a picture. So let's say I have 0 here, and here's -1, and here's 1. Let me get a different color. X1 is here, and then x2 is here, x3 is here, and then x4 is here, and then x5 would be, what would x5 be? It would be -1/6, so it would be, somewhere over here. And as you keep increasing this, all the terms are going to start bouncing up above and below 0, and it looks like all the terms are heading towards 0. Whenever you look at a sequence and you see that, Whenever you look at a sequence and you see that all the terms appear to be approaching some fixed number, we say that the limit of that sequence is that number. So in this particular case, we say the limit of the sequence x is 0. In particular, I can get arbitrarily close to 0 if I follow the sequence xn up here. I can get arbitrarily close to 0 by simply taking n to be sufficiently large enough. Okay, so let's give this idea of a limit of a sequence a precise definition. So, definition. multiple definitions. For a sequence x of real numbers and a real number L, we say x has limit L, or if you want to be fancy schmancy, x converges to L. If and only if, for any epsilon greater than 0, there exists a natural number n such that if I take a term in the sequence that's farther than that natural number n, then for all of those terms that are indexed by a natural number bigger than capital N, the distance between the term in the sequence and your limit is strictly less than epsilon. When x converges to L, which is a real number, we write the calculus notation that y'all are probably comfortable with. The limit as n goes to infinity of x sub n equals L, or we write xn and write this arrow L. If such a number L does not exist, so if no such number L exists, we say x diverges. Or in the calculus way, we say the limit as n goes to infinity of x sub n does not exist. Okay, so this definition, I mean, students sometimes struggle with it because it is quite technical. But let me draw you a picture. Actually, let me before I draw a picture, let me just say it in words. Say I have a sequence, okay, and say I have a sequence that looks like something as the follows, okay. So I have some sequence that looks like this. And then right here I have L, which is going to be the limit of that sequence. What does okay, so let me just write down that this, let's say, is x1, x2, x3, x4, and so on and so forth. What is epsilon? So what you're going to say is, say I have the sequence x1 through, I have the sequence x right here. And what does it mean for it to have a limit L? So say you come to me and then you say, I want you to give me numbers, I want you to give me terms in this sequence that are closer than epsilon, that are less than a distance epsilon away from L. And I would look here. So let's say, for example, you give me an epsilon and you say, I want all the terms of the sequence that are within this distance of the limit. And then I could look at the sequence and I say, okay, I can't give you the terms x1, x2, or x3, but it seems that if I take all the terms above 4, all of those terms are going to be a distance less than epsilon away from the limit. And then you come to me and then you say, okay, wise guy, what if I give you an epsilon that's this far away from L? And then say, I want all the terms of the sequence that are less than a distance of epsilon 1 from the limit. And then I look at my sequence and I say, yeah, I can give you some terms. I just have to take n to be sufficiently large. So now 4 doesn't do it. I have to take some terms bigger than 4, 5, 6, 7, 8, maybe 9 or 10. And if I index all the terms of the sequence that are indexed by a natural number bigger than, say, 10 are going to fall under this interval of really just length 2 epsilon 1, but are within a distance of epsilon 1 away from the limit. And if I can do that for any epsilon that you give me, right? If I can find a natural number such that if I take all the terms that are indexed by bigger natural numbers and it falls within that distance from the limit, then we say that that limit converges, right? So no matter what epsilon you give me, if I can find a natural number such that terms of that sequence are within that distance that you gave me from the limit, then the limit of that sequence exists, and it is that number that we've been discussing. Okay, so hopefully that wasn't too confusing. It can get a little technical, but that's the idea. Is I give you a sequence and I say the limit is L. In order to prove that, you come to me and then you say, okay, well, find me all the terms that are within a distance away from the limit, and if I can give them to you no matter what the distance you give me is, no matter how arbitrarily small it is, that means that limit exists. Okay, so how does one prove this? There is a formal proof method to do this. So proof method, and I'm going to write formal here because this is formally how to do it, but as we'll see, actually proving, so writing is actually seeing the proof of the limit of the existence of the limit of a sequence is not so useful as much as the scratch work that's involved. But this is in general how you start a proof. You say, let epsilon greater than 0 be given. Right? So this is the distance that you came to me and said, okay, I want you to find all the terms of the sequence that are less than epsilon away from the limit. Okay? And then you specify how to choose your natural number. So choose n equals something. And this is going to depend on epsilon. And then you're going to let n be a natural number with n bigger than that number that you've chosen. And I'm going to put 3 dots here. This is going to involve important scratch work. And really the meat of these proofs go into these important scratch work parts. Important scratch work. And then after you do the scratch work, you conclude, therefore, the absolute value of xn minus L is less than epsilon. So the limit as n goes to infinity of xn equals L. So any proof showing the existence of a limit and showing that the limit of a sequence is L must be written in this format. But let me show you why the meat, the scratch work is really the important part of these proofs. Okay, so example. We're going to go back to an example that we talked about before. So show the limit as n goes to infinity of negative 1 to the n over n plus 1 equals 0. Okay, so we want to prove this. We want to prove that the limit as n goes to infinity of this sequence is indeed 0. And now, so you might, this is actually relatively easy to do, you might think, from your calculus days. But, everything that you learned in calculus, that's not a real proof. Those are just sort of quasi-proofs. This is going to be a real proof, mathematical rigor. That's what makes analysis both frustrating and beautiful, is that everything is rigorous and everything can be, every claim can be given error bounds, and everything can be given a rigorous proof. But it's also beautiful because it gives absolute truths about the numbers, and that's kind of a humbling and beautiful thought. But, okay, so what do we need to do to show this? So let's write down some scratch work. So what do we need in order to show this is we want xn minus L to be less than epsilon. That is, we want the absolute value of negative 1 to the n over n plus 1 minus 0, which equals the absolute value of negative 1 to the n over n plus 1, which actually equals 1 over n plus 1. We want all that to be less than epsilon. Now, if I solve for little n here, what do I get? I get that n must be greater than 1 over epsilon minus 1. And so this little scratch work here shows us that need to choose capital N equal to 1 over epsilon minus 1. Or bigger than or equal to 1 over epsilon minus 1, because 1 over epsilon minus 1 might not be a natural number. So we just need to choose the natural number n to be bigger than 1 over epsilon minus 1. And if we do that, according to this little scratch work calculation, we'll have that for any epsilon greater than 0, we'll have that the distance between the sequence, we'll have that the distance between the nth term of the sequence and the limit is less than epsilon. And so we've basically done it. Now we just have to write down the formal proof. So proof. Let epsilon be greater than 0 be given. Choose a natural number capital N with n bigger than 1 over epsilon minus 1. Suppose n is bigger than capital N now. Then, what does that mean? That means n is bigger than 1 over epsilon minus 1. So, 1 over n plus 1 is less than epsilon, just solving for epsilon, really. Which means the absolute value of negative 1 to the n over n plus 1 minus 0 is less than epsilon. So for any epsilon greater than 0, I found that I can get this sequence to be arbitrarily close to 0. Therefore, the limit as n goes to infinity of negative 1 to the n over n plus 1 equals 0. Okay, and this proof might seem like a little bit of magic, and now I think it's clear. The proofs of these statements is actually not so clear. Like if I just wrote this down as the proof of the limit, you might have a lot of questions, like where did this 1 over epsilon minus 1 come from? what are all these weird inequalities he's writing down? How did he jump from 1 over n plus 1 and jump to absolute values and so on and so forth? But that intuition is given to you by doing the scratch work. And so it's important to look at the scratch work. Okay, and so here's a nice theorem here. You might be curious, like, can a sequence ever converge to more than one number? Well, this theorem says no. If a sequence X converges, then the limit is unique. And you can prove this. The proof is a little bit technical, but okay, let's just go through it. It is a uniqueness proof. And so what do you do in a uniqueness proof is you assume that whatever you think is a unique is not unique and try to run into a contradiction. So suppose xn goes to L and xn goes to M and L is not equal to M. Let epsilon be equal to 1/3 times the absolute value of L minus M. And so what is this weird choice of L minus M? Is we're going to try to choose epsilon. We're going to choose epsilon so small that any point in the sequence cannot be within epsilon of both L and M at the same time. Okay, so since xn goes to L and xn goes to M, there exist natural numbers n1, n2, such that when little n is bigger than capital N1, the absolute value of xn minus L is less than epsilon. And when n is bigger than capital N2, we have that the absolute value of xn minus M is less than epsilon. Right? So let n be max, the maximum of n1 and n2. And suppose n is bigger than n. Okay, so n is bigger than both n1 and n2, so that both of these inequalities that I'm underlining now hold. In that case, the absolute value of L minus M is going to be equal to, I'm going to do an add and subtraction trick, L minus xn plus xn minus M. Okay, that is going to be less than or equal to, if I break these absolute values apart, that's what I get. And absolute values, I can now play with I can negate the inside while maintaining equality here. So I have that this is a sum of xn minus L plus xn minus M, both in absolute value. And now we know that both of these absolute values, these terms in the absolute values, are less than epsilon. And so I get that this is less than or equal to epsilon plus epsilon, which is equal to 2 epsilon, which is indeed equal to 2/3 times L minus M, which means L minus M is strictly less than 2/3 L minus M, and this is a contradiction, so L equals M. So it must be the case. And so the limits of a sequence are unique. Okay. Sometimes you can just look at a sequence and then you'll know like what the limit of that sequence should intuitively be. You can just look at them and you'll know. But other times it's not so clear. And so in general, it's a good idea whenever you look at a sequence and you have a good idea as to what you think the limit of that sequence should be, it's a good idea to always check on a calculator or something to make sure, some computer program to see if that's indeed true, because many times sequences can be deceiving. So for example, the limit as n goes to infinity of 1 plus 1 over n to the nth power, right? I mean, you might be tempted to say that this is just 1, but this is actually equal to e. And so you just have to be careful with these things because you don't want to get the wrong idea from, just from, I don't know. So sometimes you can look at these things and they're not so clear. But yeah, so this limit, for example, if you aren't careful, you might think this is just 1 because 1 over n gets vanishingly small, and then you're just raising 1 to a large n power, which you think is maybe just 1, but really this is e. Okay. So I'm going to write maybe deceiving. Another example of a sequence that maybe is not so deceiving and is quite trivial is just let k be a fixed real number and let the sequence xn just be k for all n. Then I think it's clear that the limit as n goes to infinity of xn is just k. If you just take the limit of k over and over and over again, it's just going to be k. Another type of sequence that is quite easy to understand is a sequence of rational functions. So for example, let's say xn is equal to 12n to the 4th plus 5n plus 1 over 70n squared minus 18n to the 4th. And you want to know what happens as n gets large. Well, as n gets very, very large, 5n plus 1 gets very, very small compared to 12n to the 4th. And similarly, 70n squared gets much less than or equal to 18n to the 4th. And so for n sufficiently large, this is approximately just equal to 12n to the 4th over minus 18n to the 4th, which equals minus 12 over 18, which is minus 2/3. And so whenever you have rational functions of this form, we can quite easily say that the limit as n goes to infinity of x sub n is equal to just minus 2/3. And so on the next page here, I'm going to write down some tips. So rational functions. If order, and what I mean by order is the degree of the polynomial, of numerator is bigger than order of denominator, sequence diverges. If order of numerator equals order of denominator, limit of sequence is ratio of coefficients of highest order terms. So, a la the previous example where we had a rational function with the order of the numerator equal to the order of the denominator, and so the limit was just the ratio of the coefficients of the leading order terms. If order of numerator is less than order of denominator, limit of sequence is 0. Okay? So again, these are just ways to compute the limits, but how do you prove that that's indeed the limit of the sequence? So let's do that. So prove the sequence xn equals 3n squared over n squared plus 1 converges. And again, before we go into the proof, we're going to do some scratch work. So, scratch work. So from the tips I've written above this example, we know that the limit should be what? The order of the numerator is the same as the order of the denominator, so I just look at the ratio of the coefficients. So the limit should be 3. So we want, for any epsilon given to us, we want 3n squared over n squared plus 1 minus 3 to be less than epsilon. Now if I combine like terms, or sorry, not combine like terms, if I get a common denominator and combine this, that's going to give me what? The absolute value of minus 3 over n squared plus 1, which is going to be 3 over n squared plus 1 is less than epsilon. Which means I want n squared plus 1 to be bigger than 3 over epsilon. Okay? But remember, in order to show that a limit exists, I have to say something about how n, little n itself relates to epsilon, not how some function of little n, but n itself. But notice what I have here is a condition on n squared plus 1. But note, since n squared plus 1 is strictly bigger than n, if n is bigger than 3 over epsilon, n squared plus 1 is bigger than 3 over epsilon automatically. Okay? And so now we have our scratch work done. We know that our capital N should be 3 over epsilon, and then we proceed from there. So let's write down the formal proof. Let epsilon be greater than 0 be given, and choose capital N in the natural numbers so that n is bigger than 3 over epsilon, bigger than or equal to 3 over epsilon. Suppose little n is bigger than 3 over epsilon. Then, automatically, n squared plus 1 is bigger than 3 over epsilon, because n squared plus 1 is bigger than n, strictly. Now what do we get? We get that, therefore, 3 over n squared plus 1 is less than epsilon. And now I work backwards with my scratch work. Therefore, 3n squared over n squared plus 1 minus 3 in absolute value is less than epsilon. So limit as n goes to infinity of 3n squared over n squared plus 1 equals 3. And again, the proof itself might not seem like it's very helpful. The scratch work is definitely more helpful in this case, and especially if you sort of follow the logical progression of why I did certain things in a certain way. Writing these proofs is a lot easier. But hopefully this makes sense. So I have a sequence. Let me just take you through the steps again. I have a sequence and I claim that it converges to 3. And then you want to, you come to me and you're like, all right, tough guy. If the sequence converges to 3, find me terms of the sequence that are closer than, 10 to the minus 99th away from 3. And I can do that provided I take little n to be bigger than 3 over 10 to the 99th. So 3 times 10 to the 99th. If I can take the terms of the sequence whose indices are bigger than 3 times 10 to the 99th, then indeed I will find terms that are less than 10 to the minus 99 away from the value of 3. Okay, so it might seem like magic, but it works, and it's a beautiful thing that works. Okay. Next, what we're going to do is going to look at some situations where we try to prove that a sequence diverges. So, example. So whenever we try to prove that a sequence diverges, we don't need to show something is true for any epsilon greater than 0. We just have to show it's true for some epsilon. And so we can choose epsilon to be our favorite number, which is, for example, 1. So prove xn equals 2n diverges. So let's prove it. Assume limit as n goes to infinity of xn equals L. Okay, so we're going to assume that it exists and try to run into a contradiction for some real number L. Let epsilon be equal to 1. And again, I'm fixing epsilon here because it's not any epsilon, it's just if I can find one epsilon for which I can show that this is not true, then we've proven that it diverges. Then for some capital N natural number, the absolute value of xn minus L is less than 1 for all little n bigger than big N. Suppose n is bigger than capital N, and I'm going to take n sufficiently large so that it's bigger than 1/2 times the quantity absolute value of L plus 1. Okay, so I can choose n to be as big as I want, so if n is bigger than n, I can choose it to be bigger than 1/2 of absolute value of L plus 1 as well. Then 2n is strictly bigger than the absolute value of L plus 1. So absolute value of 2n minus L is going to be bigger than 1, which is a contradiction, because we've said that the absolute value of 2n minus L is less than 1. So x diverges. Okay. And again, I mean, this is one of those sequences where you just look at it and you're like, of course it diverges. It's not getting closer to anything, no matter, I mean, xn just grows as n, and n doesn't, and the sequence of counting numbers doesn't converge to anything, and so of course it's not going to. What about this sequence? Prove that y sub n equals -1 to the n diverges. Okay, so proof. Suppose L is a real number, and let epsilon be equal to 1. Let capital N be a natural number. Let capital N be a natural number, and now we have two cases here. Because we know that the sequence has negative and positive terms, it could be that the sequence converges to positive or negative terms, so we have to consider both cases. If L is positive, then let n, a natural number, be odd, and little n bigger than big N. Then y sub n equals -1. And the absolute value of yn minus L is going to be equal to the absolute value of -1 minus L, which is L plus 1, which is bigger than 1, which equals epsilon. Okay. If L is less than or equal to 0, let the natural number little n be even and bigger than that capital N. Then the absolute value of yn minus L is going to be equal to the absolute value of 1 minus L. Okay, because in this case we're taking n to be even, and so the even terms of the sequence, as we discussed before, are just 1, which is going to be 1 minus L, which is bigger than 1, which equals epsilon. So in both cases we have shown that when n is sufficiently large, we can find So for both cases, let me just write this out. For both cases, we have shown there exists a natural number n with n bigger than n with the absolute value of yn minus l bigger than or equal to 1. And this is true for any real number. So y diverges. Okay. Almost done here. We're going to talk about probably one of my favorite theorems in all of analysis / calculus. And that is the squeeze theorem. Okay, so let's look at this. It's an interesting theorem that allows you to understand how potentially very complicated sequences behave as n gets very large, based on the fact that you know how some simpler sequences behave. So this is also called the sandwich theorem. I like to call it the Oreo theorem. But the more correct ones are squeeze theorem or sandwich theorem. And they are the following. Suppose A, B, and C are sequences of real numbers such that A sub n is less than or equal to B sub n, and B sub n is less than or equal to C sub n for all natural numbers n. If A sub n limits to some real number L, and C sub n limits to the same real number L, then B sub n is going to limit to the same value. Okay, so how do we understand this? Say we have n here, and let's say I have a sequence. Let's say A sub n looks like this, and this is where L is, and say C sub n looks like this. So this is C sub n, this is A sub n, and perhaps B sub n is a more complicated sequence, but you know that it's between A sub n and B sub n, then B sub n tends to L. Okay? So this is what it means by you're squeezing it. Okay? So proof, there exists an there exists an n1 in the natural numbers such that when little n is bigger than capital N sub 1, we have absolute value of an minus L is less than epsilon. There exists an n2 in the natural numbers such that when n is bigger than n2, we have that the absolute value of C sub n minus L is less than epsilon. Let capital N be the maximum of n1 and n2. Suppose n is bigger than that natural number. We have a sub n is less than or equal to b sub n, and b sub n is less than or equal to c sub n, which gives a sub n minus L is less than or equal to b sub n minus L, and that's going to be less than or equal to c sub n minus L. When you take n to be sufficiently large, this tells us that minus epsilon is less than a sub n minus L, which is less than or equal to b sub n minus L, which is less than or equal to c sub n minus L, which is strictly less than epsilon, which gives us with the beautiful result that the absolute value of b minus L is less than epsilon. So the limit as n goes to infinity of b sub n equals L. Okay, so let's see this in action. So consider the sequence sine of n over n. This is a more complicated sequence to understand than the ones we've looked at, some of the easier ones we looked at. But note, -1 is always less than or equal to sine of n, and sine of n is always less than or equal to 1, which means -1 over n is less than or equal to sine of n over n, which is less than or equal to 1. Now, -1 over n tends to 0. This is a rational function, and notice that the order of the denominator is bigger than the order of the numerator. And the same can be said for 1 over n. So, by squeeze theorem, the limit as n goes to infinity of sine of n over n equals 0. Okay, so that concludes this section on sequences. Hopefully it gave you an appreciation for sequences, and hopefully gave you a solid foundation into understanding them. They are important for understanding the structural properties of the real numbers, and to sort of get a rigorous understanding of calculus in more generally, but also hopefully you can kind of think of this as a sort of a fun with inequalities section. And as I sort of said at the beginning of this lecture, oftentimes in applied sciences we're considering answers to questions that fall within a range of the true answer. And so notice in this section we were never sort of adamant in saying something equals another thing. We always say that, well, all the terms fall within a range of the true answer. And that's a very important way to think about things, especially when you're working in applied sciences. So that concludes our coverage of Chapter 4. I'm not sure exactly what I'm going to do next, but keep watching for YouTube videos. I hope you enjoyed it. Thanks for watching, and I hope it was insightful. Peace out.